What's up, everybody? Welcome back. Today we are writing a memory allocator. Um, and I guess that there's no like subtopic. That's what we're doing. We're writing a memory allocator. So background here is I've been a little bit annoyed that when I run coverage reports on my image editor, I see a big bunch of red lines. And the big bunch of red lines are all of these like error differs, these error handlers for when something goes wrong, right? In this language, memory allocations can fail. That's one of the many things, but other things can fail too, right? File IO can fail, whatever. And error defer blocks let you say, okay, if something fails, like maybe we were trying to initialize something and we were going to store all of this stuff in it, but now that like something failed during construction, we have to make sure to free all of the stuff that we made, just just in case, right? So that we don't like leak memory and stuff. And the problem here is that sometimes I typo, right? And sometimes I free the wrong object, which means that we're going to double free and leak something. Both not very good, right? And so like ideally, maybe the answer to that is, well, we shouldn't just commit code that we've never run into our code base. I was like, that's pretty reasonable. I don't think it's really reasonable to commit something that you've literally never touched. Like that's insane. But it's kind of what you got to do unless you find some way to test every single one of these error differs. And it's like, okay, well, is there a way we can just like delete these things? That seems kind of nicer. What if we just said no more error differs in here? And it's like, okay, so what are these error differs for? Well, the vast majority of them are to clean up allocations of something like down here, right? So we're constructing this renderer. And we go, okay, well, there's all this stuff that we want to allocate inside the renderer, and we're going to clean all of these up. But if we just didn't have to clean them up, then these error differs just go away. Because somewhere above, up in the sky somewhere, we're going to go, okay, let's free the renderer. And so if in both the happy and sad path we could do the same free call, that'd be pretty sick, right? And so that kind of brings us into this world of like arenas and that type of stuff, right? Where you have like some allocator where you say like, I have some pool of memory, and this is my like pool of memory for the renderer, right? And like all things that when we're constructing the renderer go into this pool. Wow, sick. And then if this thing fails to create, we nuke the pool, great. Or if the thing does not fail to create, later we'll nuke the pool when we close it the natural way. So now our like happy and sad paths are like kind of in the same spot. And so what I kind of wanted when we were like experimenting with this idea yesterday is I feel like what I want like a tree, hand wavy. I want like something that's like, app. App has some like a bunch of like an allocator associated with him. And app has like things below him, right? He's got like a GUI framework and he's got like a renderer, right? And in the GUI framework, the case we were hitting was that we have like a sidebar. Maybe calling this a GUI framework is wrong. We'll just call it the GUI. In the GUI, we have a sidebar. And that sidebar has like content in him that like gets reset. So we like allocate room for all of these widgets, all of this text, and then we go, oops, this is the wrong object. Delete all that. Let's make a new one now. Right? And so what I want is the ability to like reset all of the memory for this sidebar, but also when we're finished with it, it would be nice if when we kill this guy, all of the memory feed with this goes away as well. And so that's kind of what I want. And the idea of like arenas does not really fit well with this, right? Because like an arena, typically what they do is you have like memory and you have like a pointer here, and then you go, okay, when I allocate memory, move the pointer forward, and when I free, just shut the fuck up, right? We're not going to do anything. And then what happens is eventually you're supposed to say, okay, now I'm going to reset this arena back to the beginning because everything that was allocated for this is no longer relevant, right? So you can imagine the case where maybe you're writing, I guess in the case of our image editor, we're doing a bunch of things every frame and we're rendering stuff in that frame, right? And so you could imagine that like all of the allocations for that frame will just go away at the beginning of the next frame. And you could imagine the same thing for like you're servicing an HTTP request, right? Some stuff comes over the network, you go, okay, I'm going to like do all this stuff later, don't care about it, bye-bye. Right? That works great. But for our case, it does not work that well. Maybe it would work that well if we wrote our whole app around this idea from the ground up. But right now, we have tons of stuff that like expects to be able to free memory, right? So we might have some like array list somewhere, array list, which is like I will allocate a bunch of memory and I will put stuff into it, and eventually I'll run out and I'll reallocate this bigger chunk of memory and I'll delete this and I'll put more stuff in here. And every time it grows, it gets bigger and bigger. Boom! In an arena, all of this gets wasted. And in our world, if we want to make like an incremental improvement here, we need something, right? And so that brings us to, okay, well, if we wanted to write a tree of general purpose allocators, I don't really know if that would do what I want, or even if that's possible, right? Or like, I don't really know how to design this tree, and I suspect that understanding how a memory allocator works will help me do that. So that's how we got here. Also, it's fun. More importantly, the real answer, it sounds fun. Okay. So that's what we're gonna do today. We're gonna try to write a memory allocator. Maybe we'll try to hook it up to our image editor, and like then we'll be able to like inspect how much fragmentation we have and stuff like that. But let's just start by writing like a simple memory allocator and see what happens. Yeah. So plan of action is like, let's get some memory from the system. Let's try to like do some form of allocations. Maybe we start with like an arena or a bump allocator and we kind of move forward from there. At some point, we're going to be like, oh shit, we want a free memory. So like, how do we store stuff in order to do that? So we'll have to figure that out. Then hook up to SVIMP and inspect in some way, shape, or form. That's kind of the plan. And we'll see how it goes. We'll see how it goes. You keep picking up things that I've done before. Okay. Wow, you're so smart. I know that's not what you're saying, but yeah, I think that I think that a lot of these things just tickle the same kind of tickle the same thing for a lot of people. You know, like there's just like this brain worm that I have, and I'm like, I want to do this thing, and that seems interesting. And like surely other people have found these interesting things as well. Oops, other way. Yeah. All right. Let's make a new project, a little allocator project that we can play in that will eventually become part of our bigger project. That's kind of the idea, I think. Let's start here. So let's make a main return error hello. Zig build. And not to brag. Yeah, I know. I was just giving you a hard time. Like decades ago. Oh, geez, that's a long time. Okay. Boom. Error hello. Hello. Okay. So I guess step one is to get memory from the system, which if we just go and we cheat a little bit, just a little bit, and we look at Zig's general purpose allocator, they somewhere, or maybe it's their page allocator. I think the page allocator is probably where I want to go. This guy somewhere does a little bit of an mmap, right? So what we can do is we can say, hey, Linux, could you just like give me some fucking memory, please? And he can do that for you. We can just be like, mmap creates a new mapping in the virtual address space of the calling process. The starting address for the new mapping is specified in attr. Length argument specifies the length of the mapping, which must be greater than 0. If the address is null, then the kernel chooses the page-aligned address at which to create the mapping. This is the most portable method of creating a new mapping. If attr is not null, then the kernel takes it as a hint about where to place the mapping. On Linux, the kernel will automatically pick a new nearby page boundary. If another mapping already exists there, the kernel picks a new address that may or may not depend on the hint. Okay, cool. The contents of the file mapping, as opposed to an anonymous mapping, see map anonymous below, I assume map anonymous is what we want, are initialized using length bytes at offset in the file. Right, so we're not reading from a file. So mmap allows you to either create a new chunk of virtual memory that's backed by like memory or by a file, right? Because so you can do that to be like, I'm gonna mmap this text file and then just like write into it like it's like a piece of memory, and then that like change will show up on disk, which is kind of sick. But I believe that's not what we want. We want the other version. So I believe that's probably what they're talking about when they say map anonymous. Mapping is not backed by any file. Its contents are initialized to 0. File descriptor argument is ignored. However, some implementations require FD to be -1. Okay, cool. So what are we expecting to have to do here? Sorry, this was somewhere else. Just get out of there for a sec. We'll pretend that, shh, we saw nothing. We'll get into another shell here, and I think what we're expecting to do is, I guess, oops, oops, we're expecting to do something analogous to mmap with a null address. Maybe in the future we're going to want to give it a hint to keep our memory segments kind of like semi-contiguous, right? I don't know if it really matters, but it might, because these are like virtual addresses. So like I think the way it works, I could be wrong. I'm kind of making this shit up, right? But what I understand is that you have like RAM, right? Little RAM sticks, and maybe you have like several of them, right? And these are like connected up to some sort of like memory management unit, right? Or well, let's assume that we're talking about like a desktop or laptop, not like some like ARM board, because I don't really know if MMUs are like, I don't know if they're always used. Some in some cases you might just get the RAM like directly on the bus and plug the bus directly into your processor. But for now, I think that we have some sort of memory management unit. This thing goes over to the CPU, right? My understanding is that uh, let's just take like the simplest example. I want to run a program, right? On my computer, I want to run a program, and if I look at like a program on my computer, I think we do like read elf -h zig out bin svimp, and we can see here the entry point address of this thing is 0x10dd920. So in this binary, we have asked like Linux, the operating system, to like literally just jump to 0x10dd920 when it loads the process. And so that kind of indicates if you didn't have like, if you just looked at this memory directly, right? Or like the bus that the memory is on is probably like a more accurate way to say this. If you looked at the bus that the memory is on, you could only run this program once, right? Because like if you try to run it twice, it would be like, wait, what the fuck? The program's already there. Or I guess that would probably kind of work because the two versions of the program would probably have the same like code. But say you wanted to run two programs and they just happen to have the same start address. Every program on your computer would have to have a different start address and be loaded into a different segment of memory or something, right? So that's no good. So what they introduce is this concept of like virtual memory, which says basically I'm as the CPU, when I like task switch between like processes, right? I've got like program A and program B. When I switch between them, I can tell the memory management unit like, yo, this guy when he's if I tell you get the thing from 0x1000, actually get the thing from like 0x cafe food, right? Like actually go get that, right? And when I tell you 0x2000, like actually go get this other thing, right? So like everything, let's pretend we'll ignore swap and paging or whatever, or swap and like what do they call it on Windows? They call it something that's not swap on Windows, right? But just like pretend we don't have page everything. We have enough memory to hold everything. Now we're free to like choose the same addresses for each program and then map them to like a physical address completely different, right? So that's what I'm talking about when I said mmap is giving you virtual memory. So sometimes you might want to give it a hint here so that your like memory locations are like close by, maybe for like a reason, but I don't think the reason is that they're actually contiguous in physical memory. It's possible that being contiguous in virtual memory is still good for like cache lookups though. Maybe. I could see a world where that's true, right? If like you're like, what the fuck is going on? If you're like stashing stuff, you're like holding a little bit of RAM over here. You're like, oh, I'm gonna look at some stuff over here and I'm gonna copy it into here. I guess maybe like if the memory management unit is like expecting to just go forwards in addresses, which is very common for things like arrays and vectors, right? Then like maybe things being like contiguous in memory is still useful because that lets this guy do his job better, but I'm not really sure. So there might be a reason that we want to do that. I don't really know. I'm theorizing about what those answers could be, but for now we'll just say, fuck it, I don't care, right? Then we're expecting to put in a length. I suspect that we probably want something that is at page sizes, right? Because we saw in the mmap man page, it said something about page aligned. I think we saw something about page. The kernel will pick a nearby. Yeah, if the kernel chooses the page aligned address at which to create this mapping, right? So that kind of implies that if you request anything less than a page long, you're kind of wasting memory, right? Because if it can only give me memory addresses every this far apart, and we only ask for this far, then next time it has to only give us this far and only this far, right? So, I don't like what that's turning into something bad. But like, so I suspect that we need to know the page size. I don't know if we can like get that from somewhere. I'm pretty sure that like on every every Linux system, it's like 4K. But I know that I think I saw in some like blog post by those people who reverse engineer the new MacBooks, the ARM based MacBooks. I think that they said that they had 16K pages instead of 4K. So is there somewhere that I'm supposed to like retrieve that information on Linux? Linux get page size. Get page size. Okay. This is like a C call though. But like, where does this come from? Can we just look at like the implementation of this in like Musel? Get page size. Like, what the fuck do? They just return page size. Got it. And where does page size come from? Okay, so I'm assuming that this comes from like the Linux kernel, probably. Probably there's some sort of kernel header. Some architectures support multiple page sizes. That's crazy. That's crazy. Is there okay? But I guess that means that there's probably a Linux system call associated with this thing. Which they're here they have nr get page size, which is not what this is doing. Nr get page size. Yeah, this isn't used anywhere. But I assume that there is like a Linux syscall associated with this thing. Isn't it a constant in the kernel? I mean, whatever. This thing said that it might not be. Oh, I see. So these architectures do have it, but the vast majority just use the page size macro. Is that using ctags or etags? I'm pretty sure it's using clang d. Pretty sure. Oh no, wait. I was just grepping. Okay, whatever. Let's see how Zig's allocator does it. Where am I trying to go? Here. What do they do? Page allocator. They aligned len comes from mem page size. Ah, nice. Wait, okay, so we can just use this. That's kind of hype. Ah, yeah, so this is what I was talking about. That 16K page size, that's in here. So yeah, we'll just use that. Okay, so this we're expecting to be stud mem page size. Hell yeah. So what was prot? Did we ever get there? I don't think I remember reading that. Prot. So this is so we probably want read write, right? If we want prot read and prot write here. Flags were okay. So what type of mapping are we talking about? Shared mapping, share this mapping, updates the mapping are visible to other processes, mapping the same region. We don't give a shit about that because it's like local memory, like just memory should not be visible by other processes in that case. So private updates the mapping are not visible to other processes, mapping the same file are not carried through. What about like anonymous? The mapping is not backed by any file. So these, I guess, are Flag's argument. Are these guys, do I have to put one of those? Can I just write like anonymous? Because anonymous feels like just what I want. I suspect we write map anonymous here. File descriptor -1 and offset 0. This is my guess as to what we're supposed to do. So let's look again at the Zig implementation of this thing. So they did write type private here. Okay, so maybe they need at least one of those three, which makes sense. But I was kind of hoping we could skip it, but maybe not. Okay. Let's get a fucking page in memory, baby. Null, stud mem page size, and then it's like gonna be stud posix prot read. And then is this thing, yeah, we can just OR these. prot right. Okay. And then what did he do? He did like something that was like map anonymous. This thing takes in a system map, which is so type is required to be put in an anonymous string. Sure. So here we're just like type is equal to private. Yeah. And then anonymous equals true. That's what we're doing here. And then file descriptor -1 offset 0. Okay. And then let's just double check if that's the same thing that they did. I just wanna be sure. Stood heap page allocator. So they use a hint, sure. Aligned length, sure. Read and write, anonymous. Yeah, okay, that's all the same. Sick. And then it looks like this thing can fail, so cat. I guess we'll just write try here. Okay. And then I guess we can like cast this to a slice. Data is, some this stuff that's like pointer cast page. I think there's some way to get like there's some way to like turn a pointer into a length pointer. I can't remember what it is though. Span, I think. Takes a sentinel terminated pointer. That's not a sentinel terminated pointer. How do I like manually construct a slice? You know? Do I do like this? Like some sort of point oh, I guess I just do it's like page from 0 to stood mem page size. Of course. Well, actually, it's kind of weird to me that the arena allocator uses prot read write. I remember some presentation that said you should always use prot none and then always switch to read write as you allocate the memory that you get. Oh, that makes a lot of sense actually. Yeah, that's kind of hype when you say that. Let's put a note here. Maybe remap from none as allocated because you want a segfault. Segfaulting is hype. We love segfaults. Yeah, but okay, let's say that we just have some data here, and let's just say that like data 10. Can we just write like mem copy data from 0 to 13 is like hello world? I think that's the right number, and then can we do like a little print of data? All right, let's see what happens. Hopefully, zig build and zig out bin is phallic. Okay, so this is mad because POSIX doesn't have, oh, it's prot dot right like this. Cannot memory copy to constant pointer. Oh, oops. No, they don't match. Is it 12? HELLOWORLD space 11. Okay, there we go. So we do have some memory given to us by the system, and we can in fact write to it. So that's kind of hype. That's kind of hype, and we can read back from it as well. So that's step 1 complete. We have a page mapped. And now let's try to do something like create an allocator out of this guy. So maybe we'll call this, instead of small allocations, we'll call it like create allocator interface. So I think that our basic allocator, we probably just want to do something that's like, we'll start with like a bump allocator, I guess. So let's say that this is like just a function that we call like get page, alloc page or something, and he's gonna return us. Maybe we can even say that it's a page that is. I guess it's just like this. I guess it's just kind of like this. I guess we kind of know its alignment as well. We could put like I don't remember where the align goes. Maybe here. Like we kind of know this is true of this slice that we get back. So let's just do this. Boom. Const page, and then we return this. Okay. I guess probably we will eventually want to free pages too, but we'll think about that later. Okay. So here, I guess we're going to have some amount of pages, right? So like, I guess here we might want to allocate more than one page. This is kind of like the minimum page size, but we might want to allocate like a bigger section. So maybe we can say like map pages, and here we will say size, and we probably want to do something like round up to the page size, right? So how there's probably some sort of like shift trick that you can do to get this right, probably, right? Because we know that the page size is going to be like some sort of power of 2. So there's probably some trick you can do there. I actually wonder, like, if we knew if it was 4K off rip, you're saying align forward? Is that in the Zig standard library? Right, like if we knew, if we were given like the number like 0x50, right? And we knew that this had to be a multiple of like 0x100. How would we do that? I guess we would do some sort of like round up thing where we do like, hold on, we can get there. You add this and then truncate, then like shift down and then shift back up or something. Yeah, you do like this divided by 100. You do like something like this. I'm pretty sure that's how this is supposed to work. You're saying that this already exists, align forward. And then hopefully if you do know that this 100 at compile time, then the compiler can optimize this into like the correct like shifts instead, which it should be faster. Align forward. They actually have align forward log 2 here, which does probably something similar, right? So they this is the alignment, this is the address. So the address is like the thing. Oh, I see. So they just is this like converting it into log 2? Align forward here. What's his source look like? Dude. Align backward is like, sure. What's align backward? That's a good trick. So align backwards just says, yo, just like truncate down, and then align forward, they just add a bunch of number to it first, so that this works. Cool. Yeah, sure. So, and then what is like, okay, round address up. The alignment must be a power of 2 and greater than 0. Okay. So we take the size and we say the like align size is this, and then the alignment is stood mem page size. Boom. And so then we allocate the align size here. And I guess that means this alignment is correct, but now this is going to be of the align size. Boom. Okay. Okay, cool. So now if we were to like const data is equal to map pages, you know, 1, 2, 3, 4, 5, what do we get? Align forward is pissed off about something. We forgot a T. All right. This guy needs to be available. That makes sense, which means that this guy needs to be available. Okay. Chill. Unused argument. I forgot to write the squiggly braces that he needs. All right. So we got 16384, which is the next page aligned thing of 1, 2, 3, 4, 5. Pretty hype. And so if we did 16384, does it do the right thing here? Does it still give us 16384? It does, and we do 16385. It should jump us forward another 4096. Yep, okay. Things are working right. So many different formulas for alignment. Odin has something like this: align equals size plus alignment minus 1. Align equals alignment minus alignment over percent alignment. Yeah, I can see that. You might want to change that print to an 11. Yeah, that makes sense. Makes sense. Don't want to just go out of range. Okay, so bump allocator. Presumably, we are going to have to return some sort of allocator of this thing, right? So stood mem allocator is going to be our output, which means that we need to figure out what the fuck this thing is. So it looks like it's just a pointer and a v table. Okay, so here we have those things. Our allocator, he's probably going to have some sort of internal state, right? Surely, right? So I think return something that has pointers equal self. That makes a lot of sense. But then what about the v table? This is kind of unknown. Bump. Can we just look up like allocator v table or something? Then we like do const allocator v table here is equal stood mem allocator v table. And what do we have to do in this thing? Alloc is optional. Resize is not optional. Oh no, sorry. Alloc is not optional. It's that he can return an optional thing. Okay, so all three of these things are required. Okay. And we can even maybe read these comments to try to get a feel for what Zig is expecting from us. So attempt to allocate exactly len bytes, align to 1, shifted left by pointer align. Ret adder is optionally provided as the first return address of the allocation call stack. If the value is 0, it means no return address. Okay. So I guess this is going to be bump alloc. Surely. I guess. Okay, resize. What's he supposed to do? Attempt to expand or shrink memory in place. Buffline must be equal to the length requested from the most recent successful call to alloc or resize. Buff align must be equal to the same value as passed in his pointer line. Result of true indicates that the resize was successful, and the allocation now has the same address but a new size of new len. False indicates this blah blah blah. Okay. False indicates actually they could not be completed. Okay. That's simple as well. And then free is just, I assume we free the memory. Okay. So I guess we actually have to implement these functions. Which is a hard life for us, but we can get there. We just copy paste this again. Paste it down here. Delete all the comments. Kind of fuck those things. Oopsies. A little too far. A little too far. And then we do a little macro to go here, jump to here, paste, go back, delete a couple of words, go to the end, and put some curly braces. Hell yeah. Okay. Okay, so allocate. I assume that like we are going to if we're doing a bump allocator, the workflow is we get some memory. This is like a page. We start here and we eventually go forwards and forwards and forwards and forwards until we get here. Boom. Then we're like, ah, fuck, we need a new page. And so I guess we either try to expand the current page, which I don't know if is allowed, or we create like a new page. So I wonder if you can mmap expand page. Is that like a thing that you can do? Mmap enlarge anonymous mapping. Is that like a thing we can do? Maybe we'll ask the idiot. Can I increase the size of an anonymous mmap mapping? Question mark. Bro. I'm writing a memory allocator. I have allocated a page of 4K with mmap. Is there a way to expand that to 16K? Okay, so if you're working on a memory allocator, it's not illegal. mmap considered dangerous. Mremap is the call that we're looking for. So I guess what we do here is if we get here, we try to expand the mapping. If it expands, hell yeah. If not, then we gotta, I guess, point to a new page. Probably we go over here and there's like a new page over here, and then we start bumping from there. Which means that we need some sort of like dynamic memory for our actual page, our like okay, so I guess if we do this as like a linked list of pages, then that means we don't need to allocate any tracking data. But the other option is that we go like pages is, this, right? And then basically we have like a pointer like cursor, I guess is the word for this, is actually going to be like a W size. Page offset, right? This is kind of what we would have in here. So the problem with doing this is if we are the allocator, it's hard for us to dynamically create this thing. Is page the term we want here? Block seems better. Yeah, you're right. Because it might not be a single page. Yeah, you're right. You are right. Okay, so the other option here is that if we run out of room in our yeah, my gut says it makes sense to just throw a pointer at the end. The problem there is if somebody asks for like a page size allocation, then we can't fit it because we need to reserve 8 bytes at the end for our tracking data, which kind of sucks. But maybe that's fine. That's probably good enough for now. If you implement resize and remap, you're already better than the STD's arena allocator because it cannot do that. Hell yeah. It almost makes me feel like, weirdly, actually, yeah, this is fine. Okay, so let's not do this. We'll have, do we want the list to be doubly linked? So that we can go backwards? How are we going to later say that we want to release memory? I guess probably every single block that we have, we need to be able to walk them. So we could, I guess we only need to store the root block. And then current block. Right? And then if we kind of like link between them with a linked list, then we're kind of chilling. We don't have to kind of store anything else, I think. Seems kind of reasonable. So I think it's reasonable also that when we construct this thing, we get a page off rip. But I guess it does, like what your initial page size is kind of depends on your first allocation, right? If my first allocation is mega big, then it would be silly for me. It would be silly for me to allocate something small up front. Is there, can we like hide this information somewhere? Ah, fuck it, it's fine. We'll just say, we'll just put this in a null. I guess it's current block. We could do it like this. Root current, and then equals null like this. It seems like a shame. It seems like a shame to null check this every single fucking time just because it might be like just because of the first time. You know what I mean? It's like it feels like such a shame. But maybe like yeah, I don't know. We could also maybe do something like the cursor's initial value is stood math max int usize. This doesn't really solve the problem, but it at least means that we don't have to like store extra information in this thing. It's kind of folded into the cursor. I guess, but on the other hand, then there's like a risk that you actually run out of memory and you reset. But also, if you did that, fuck you, right? You're never gonna be You're never gonna be using that much memory. Okay. No, wait, hold on. I have a wait, but there's a better answer to this. I'm a dumbass. Hold on. We just set these guys to this off rip. That's way better. Okay, because then we can just check our cursor. We'll be like, we're out of bounds of the current block. And then we can just be like, if we're out of bounds of the current block, make a new one. Okay. Do we actually need to link forwards? No. We only need to link backwards. No, because if we reset, we want to link forwards. But if we reset, we can also just free all the pages. Okay, yeah, let's do that. We'll do that. We'll just link backwards. Because in the bump allocator, there's no reason to care about the root block. We actually don't give a fuck. Okay, cool. So what we can do here is we can just say, okay, so what is this guy supposed to do again? I guess we have like self is a pointer to bump allocator that is a pointer cast, a line cast of context. Chill, right? Then, okay, I need to read this again. Alloc is an attempt to allocate exactly length bytes aligned to one shifted left by pointer line. So that's probably what like align forward log 2 is. Right, so we probably take the length here and the pointer align. And that should give us the like aligned len, like this. Okay. Then we say if self cursor plus aligned len is greater than or equal to self current block len, then we have to allocate a new block. So we pick a block size and we can just use the aligned len here, which is probably kind of a shit metric, but that kind of means that like, you know, if we get something less than a page, we'll allocate a page, but if we get something bigger than a page, then we'll just do whatever fits. Sure. It would like yeah. There's maybe there's some sort of like minimum size that we'd want to do. But whatever. The pointer has to be aligned, not the length. But the aligned like the length of this thing, it needs to start at some alignment, right? And so in order for that to work, like you're effectively allocating more, right? In the case of the bump allocator, right? Because we have like, our cursor's here. We want to be aligned to like here. So we're kind of like just losing this memory by doing that, if that makes sense, right? Because we have to, because like we need the length that they asked for here. I think that's what that's what I would do at least. Okay, sure. Oh, but you're saying that we could just use len here, maybe? But we don't know that their alignment is going to be uh I guess yeah, you could use len here um if pointer align is less than like the log 2 of this or equal to, because then the alignment is free. Yeah, that kind of sounds reasonable. We're kind of just making it up as we go, but that seems reasonable. So if it's less than, we use len. Else, I guess we kind of use len no matter what, actually. Otherwise we have to do like some sort of like extra alignment. So let's just do this is easier. And then you can actually get crazy here, and we can do this comp time to make sure. Okay, cool. Is that equivalent to a pointer takes less than an entire page? Seems likely. Not that a pointer takes, I don't know. Maybe. Yeah, that seems quite likely, huh? Especially because this is U8. No, but I think you're kind of right. Like, when would you ever need an alignment of like 16K? Right? Like, when would you ever want that? I can't see it, but it's possible. But yeah, I mean, this is a U8, so I guess their maximum alignment is, oh yeah, that's 2 to the 255. That's a big number. We'll fucking see. We'll see if that ever comes up. Okay. So here, we need to do something with this, right? So I guess if this fails, we return null. But if it does not, then we can do something with it. So what do? We like put it as our current block. So I think here, we set our cursor to size of pointer to like something like this, because we kind of want to store that pointer in here. Yeah, I guess it's like a pointer to a U8 is kind of what we want, right? Okay. I guess technically we also know this is aligned to std_mem page size, which might help the compiler out a little bit. We might as well write that there. It might help. Okay. So I guess we say last block is self current block. And current block is this, or I guess it's actually self current block. And then we write last block from 0 to size of a U8 slice pointer. I wonder if you like std_mem slice as bytes as bytes as value. I want to like get a pointer to this thing automatically. I know that there's a way to do this. Stud mem as is it this? Given a pointer to an array of bytes, return a pointer to the value of the specified type backed by those bytes. Yeah. So here we go, like, we have a pointer to a U8 slice at the beginning of last block. And we say that this is equal to current block. That sounds kind of hype. I guess it's more like the address of current block. Ah, fuck. Interesting. So this gives us back a thing. I guess we kind of want this, actually. We want to put the slice directly in here. Yeah, not a pointer to the slice. We want the slice itself to be current block as well. All right, yeah, wait, that seems reasonable. And then now we have, I guess we also have to reset the cursor. Okay. And then here we actually need to ask for len plus size of a U8 slice. Because we are going to put that at the beginning of the fucking page. Yeah. But it actually needs to be aligned forwards here. So we actually want to... This is tricky. So we want to allocate len from the cursor, from like whatever block we're at, right? We want to allocate this much, which means that we need to align. We need to take the cursor and move it forwards to the alignment, then add the length. Which I think is what Crimson Dawn is probably said here. But yeah, I think that is what we have to do. So can we like cursor aligned, like len with aligned cursor? Probably is like we're looking for length and this like pointer alignment, right? And we're gonna take the cursor as well, I guess. And this is gonna return a new U size. So we're gonna do align forward log 2 of cursor to pointer line. Is this even what we want? Maybe we just do like align cursor. In which case we might as well just do this. Yes. So I guess this is like alloc start. Okay. So we have like this allocation start. Then we have len. Alloc end is alloc start plus len. Okay, that makes sense to me. If the alloc end is greater than or equal to the current block len. There we go. We're getting somewhere. Okay, so if the allocation end is greater than or equal to the current block, then we got to do some fucking work. I'm just going to put this assertion here, I guess. Doesn't really fucking matter. Okay, so then this math probably changed. The amount that we want to map. Oh, I guess putting it here makes sense because it's kind of, this is where it's relevant. Okay, so we want to map pages. So this is going to be different again, right? So we're gonna say like const cursor start. I guess this can actually just be like this. And maybe we even name that. We can call this like next block is equal to this, right? Um, that makes things a little bit nicer. This can now equal to cursor start. And then here, when we allocate this thing, we want to do like new page start, I guess. And this is going to be the cursor start and pointer line. Yes. This is starting to make sense. Then we say new page end is new page start plus lan. Okay. So there's like a maybe like dedupe these two lines, like name and split these two lines to dedupe with below. Okay. We can probably do it the other way here. We can probably say if this stuff is less than that, then we're like fucking good to go. So we just have like a thing to return. We just say self cursor is equal to alloc end. And we just return like self current block from alloc start to alloc end. Yeah. Okay. Then all of this comes out in indent level, which is hype. I love it when things go down in indent level. I almost want to scope this stuff so that we don't accidentally reuse alloc start and alloc end. Okay. Then here we map pages of new I guess it's new page end. And this will get rounded up. Then we set the last block to the current block, and we set the cursor to cursor start. But we actually probably just set it to new page end. And then can we just return current block from new page start to new page end? That feels pretty good. That feels pretty good. That feels like it might work. That's like a maybe. Okay, so can we we're missing a ret adder thing. What is ret adder? Ret adder is optionally provided as the first return address of the allocation call stack. If the value is 0, it means no return address has been provided. So this must be for the call trace stashing in the general purpose allocator. Like they want to know where the allocation came from, and so this is probably how they do that. So we'll just discard that for now. We don't really give a fuck. But maybe in the future, maybe in the future, fuck it. Well, I mean, we don't have to write that down. In the future, we might want to use that. Okay, so I think that that's probably enough for us to start playing with this, right? It would be interesting to see if we can actually do something with this. I'm a little bit worried about like ooming ourselves here, but I guess any checks that we do to prevent ourselves from ooming will just like are also a little scary. But it would be kind of cool if we just use this thing. So let's make a bump allocator. Bump is equal to this, and let's do bump allocator. Okay, and can we do like stood array list of, u sizes and initialize the allocator? And we'll just do like for 0 to 50. Can we do like append I and then go for 0 like items al items len, or for al items, I guess? Can we print it? So if everybody is happy, we will see the right answer here. Instead, we don't even compile. Expected pointer to U8 found U8. Oh, interesting. So it's kind of like this. In kind of both places. Okay. Then I guess here we return false here. This unconditionally does not fucking work. And then free does nothing. Okay, so this guy is pissed as all hell. General protection exception, no adjective. Because I guess if current block, if the previous block is wrong, is empty, we only do this if it's not equal to 0. But everything else, I think, is just kind of chill. Yeah, it kind of looks like it. Okay, okay. So that's a good sign. That's a pretty good sign. We've, like, got some memory somewhere used in an array list, which is kind of hype. Kind of hype. I would love to, like, look at the memory of this thing. I think that would be kind of exciting. So can we just say, like, visualize? I want to know, like, what the allocation patterns of this are, and what that means. You know? Is there a way for us to, like, easily inspect that? We could, as every time we allocate here, I generally avoid pointer cast. Slice pointer works too. Oh, that's a good point. That's a good point. It's a pretty good point. So we could write down every time an allocation happens, and we could kind of replay we could write down like the allocator state at each allocation and then visualize that somehow. So what do I want to know? I guess I want to know what our blocks are, right? So I kind of want to know what these look like. And I probably also want to know like what each allocation was. So I kind of want to know like so if we were given a block of this size, it would be nice to know that we allocated this much stuff and this stuff was totally ignored. Because like it was like on a boundary or something, right? Am I right that discards that Zig is discarding the end there? I don't know. I was putting the end there because like I wanted to make sure that like if it doesn't do that, then it would be kind of nice if we like assert like I could see a world where it creates this slice and then Zig goes, "What the fuck? This doesn't fit." That's kind of what I was thinking when I did it this way. But you're probably right that we could probably do something else a little bit more clever, right? You might be able to do like self current lock, maybe like plus new page start or something. Maybe you could do something like that. But I was just kind of hoping to get like some sort of like extra safety here. And then I kind of figure that like in release mode that the compiler will probably figure that shit out for me and be like, oh, this is useless. Right? I assume. But what do I know? Yeah. So I guess I want to see all of the pages that we've allocated with their sizes and all of the pages we allocated with their sizes and where the allocations ended. So I guess I kind of want to write down a list of empty space is kind of what we want. Yes. Sure. And what's like the way to show this right now? I guess we can just write down like what the utilization is. Visualize is maybe wrong. Like inspect is probably the right word here. Because I don't really think it's worth like making like a little graphical visualization for this yet. Okay, yeah. So every time we allocate, let's write down new page start here. New page end. So I guess when we create a new page and we allocate from there, everything from self cursor onwards is wasted. So here we can just be like, yeah, maybe we can even just stash that here for now. Wasted space. And then we can also say here, we can also keep track of like the tracking overhead here. Right? And then we can track, say, total allocated. So this is 0 initially. This is 0 initially, and this is 0 initially. Okay. So when we allocate a new page, total allocated plus equals self current block dot len. Okay. Tracking overhead. Plus equals cursor start. Okay. And then wasted space is the trick here. So wasted space is equal to last block dot len. It's like current block len minus self cursor here. And then this only, we need to make sure that like this stuff only gets committed if the thing works. So the cursor hasn't been updated yet, so we can just use last block here. And then I think all of this is fine. Yeah. Okay. So then can we like inspect this thing? No. Because block len might be 0. Okay. So wasted space, we'll just do a saturating sub here. That's fine. That's like a valid case in the initial state. Okay. Oh, interesting. So here we've allocated. Okay, so this is kind of fun. So for a 50 byte vector, or sorry, 50 times 8. So 50 times 8. For a 400 byte vector, we have allocated 4096 bytes. Sure, because we allocate in at least like, oh, there's also wasted space from alignment. That's a good point. Thank you. Good point, good point, good point. Yes, we want to say probably here is equal to alloc start minus self cursor. And down here somewhere, we also want to do it. This is fine. So it's only here that we were missing. I'm pretty sure. Pretty sure. Should wasted space be cumulative? Yes. All of these things should be cumulative. Strangely, though, oddly, we actually don't see any wasted space here, which is consistent with what we see here. So all of these 170s are the things that Zig wrote in here after he was like, I'm done with this memory. So when the array list resizes here, he like zeroes out the old version of it. Then we have directly after that, we have 8-byte aligned 1, 2, 3, 4, 5, 6, which makes sense, right? Because each of these are U sizes. Yeah, so for this, simple case, we actually don't have any wasted space, assuming that we did this right, which I think we did. Wasted space is the alignment or block length movement. Okay. So it would be interesting maybe to work with array lists of different sizes here. I guess the array lists will might be too intelligent for us. Might be. I mean, I should say here though that we do see that we have over allocated here because our 400 bytes, as the vector resized itself, it ran into trouble. But also, kind of interestingly, it seems. Oh yeah, I guess we don't really know how many of these, like how many vectors were contributing to this. Okay, cool. So let's implement free. Free, there's actually no work to do. We might want like a function reset. But I mean, we can talk. Like, there's no. Maybe this is worth doing. Yeah, let's implement our reset. So, bump allocator. Let's say we're doing a bump reset. Okay. So I guess we probably want to set the current block to this, right? We reset our wasted space, we reset our tracking overhead, and we reset our total allocated, and we reset our cursor position to cursor start. Okay. Hi guys, sorry to ask this, but what is the language? It's Zig. Zig, zig, zig. And then before we do this though, we actually have to free everything. So we want to go var block is self current block. Right? While block len is not equal to 0, we have to unmap this page. So maybe unmap. Maybe we call, first of all, map pages. I think we agreed on the term block earlier. And so then we must have an equivalent unmap block, which must take in probably some sort of U8 slice and returns probably nothing. Stood POSIX m unmap. And what does this just take? It takes in the memory aligned to the page size. So we actually probably do need to write down align stood mem page size. Boom. Which is fair. And is this it? Oh, hell yeah. Wait, that's hype. That's hype. So I guess all we have to do is iterate over these blocks and unmap them. Boom. Block. And then we say next block is block what, bytes to value of next block at block. Yep. And then we say block is equal to next block. Boom, chill. Okay, so that should reset them all. So then what we should be able to do is we should be able to go like bump reset. And if we then were to try to do this again, we should segfault because he's going to be like, wait, what the fuck? I can't read that memory anymore. It might also be interesting to dump. I guess dumping the allocator state doesn't do anything for us here, but we do want to make sure that the memory that we had in use before it does in fact go out of our world. 96. I guess here we can say that our next block has the same alignment. And then even here, maybe we even just call next block. That kind of feels nicer. And then here we can write this as block as well. There. So here we do see that we segfault at the second attempt to read the array list items. Pretty huge. Pretty huge. But the reset itself shouldn't fail. Perfect. Perfect. Let's fucking go. Okay, so that's like a bump allocator that's like kind of sufficient. Kind of sufficient. And we could do a little bit more here. We could work at on like resizing the last page and stuff. But for now, I think it's probably more interesting to jump into trying to get like free to work correctly. So I'm gonna just copy paste this allocator. Couldn't you do this in one big unmap? We don't know that the mapped blocks are back to back though, right? So we have to unmap each page, each block individually, I think, because the way this is stored is not like, it's not like this. It's like we have some stuff here. Oh, we should test the block reset, huh? So can we do this to like, 4,000 or something? So, haha, this is kind of interesting. So first of all, do we, oh, the block is so big. Okay, so we do in fact see this thing go to 4,000, but if we allocate 4,000, we see that like for a 4,000 element vector, wait, was that what it was? Yeah, 4,000. We have allocated 118k for, I guess that's not that much overhead, because 4,000 times 8 is 32, so it's about like 4x, which is pretty bad. We've wasted around 9,000 bytes, 9k, with a little bit of tracking overhead, but it does look like the rest of this thing is still working. So I think that our multi-block stuff is fine. It seems fine. But yeah, so what I was trying to say here is, in this case, what we actually have, what we could do is we could write down here. On mapping block, can we write down like of length this? I think that will maybe give us a little bit of an appreciation for this. Okay, that's not good. Wait, that's not good. Why isn't this working? I was expecting to see a lot more of these, because we've allocated this much stuff. We have to unallocate all that. So we've done something wrong. That's kind of fun. Why? If last block len is not equal to 0, we get the last... You could, because you do. Yeah, good point. So why isn't this working? Why is this not working? Because it's backwards. We're fucking dum-dums. And then here, we don't even have to do that guard. We can just write it unconditionally. There we go. This is what I was trying to see. So here you see that like we have multiple pages back to back, right? So we start with one of 4096, 4096, 4096. It's weird that we have mapped 3 of 4096. That's kind of weird. The fact that we're getting duplicate sizes. Oh no, wait, that makes sense. It's because like our array list has like made it to here, and he's trying to allocate something that fits very much in this block, but it doesn't fit at the end. So that makes sense. But yeah, the storage format is like, here we have many blocks of different sizes, right? And I don't think there's like I don't think we can like do all M unmaps in one call. We could maybe, if we tracked freeze, like check if we had stuff that we don't care about and do it as we free, but whatever, it's fine. Okay, let's try to write an allocator that does free tracking. I don't know how the fuck we are going to do that. But we'll figure it out. So can we call this like general, like normal alloc is probably the inappropriate word for this. So we are going to have to figure out a storage format for this thing that makes sense. Hold on. Hold on 1 second. Let's just kind of get this guy ready to go. Okay, so this is kind of the starting state. Probably we delete all members. We don't really know what we're going to do here. But we got to figure it out. So, what I was Googling like, how do you write a memory allocator type shit. I ran into this thing. This thing felt like a pretty good initial overview. So, basically, like, how the fuck do you store, like, how do people store free elements, right? You could imagine if you were to continue on from the scheme that we're using right now, right? So we just like, we do a silly bump allocator, we start here, we move up, we move up, we move up, right? Fine. Then, eventually, somebody's gonna come and say like, okay, this area of memory is now free, right? You can use this again. So what you could do is you could maybe store this as like a linked list. So you could say that like, okay, so we have free memory from here to the end, and we have free memory here. You could like just say, okay, here's the first free block, and just like go until you find one that fits. But that seems like pretty stupid, like hand wavy, right? So people were talking about like sequential fit. So this is kind of what I just said, right? You just have like a linked list of stuff, and you sequentially search this until you find stuff. Then there's also something about like, maybe you might try to look a little bit harder. You might take like the first thing that you fit, or maybe you look a little bit harder for other things. There's segregated free lists. I believe this is what Zig's general purpose allocator uses. I didn't look too closely, but I did just open it, and I did see comments about, buckets for allocations, right? So I did see that. Where basically, if we look up like segregated free list, it's basically just saying that like we store block sizes in like chunks of something. You have some way to determine like what your block sizes are, and you store free lists of those block sizes independently. And the idea here is that like probably you reduce fragmentation, because you could just be like, oh, okay, I'm going to allocate from the 16 block segment. Okay, are there any holes in the 16 block segment? Hell yeah, I'll take one of those. Then there was this thing called like buddy system allocator, which is basically like you have multiple lists. My understanding of this, kind of skimming it, was that you start with like one big block, right? And then you go, okay, I need a 4-byte allocation. So if this is like big, right? You split it in half, you split it in half again, you split it in half again, until you get something that's like about what you asked for, right? Boom. Then when you free this thing, you go like, is there anything in the free list that's like my partner? Who is my friend? Who did I like split from? And it's like this guy. And you go, okay, he's back. He's free. So now we can kind of like merge ourselves back together. And then we go like, oh, okay. Then this guy's free too. So we can kind of like merge this back together. And then eventually you can like merge back all the way into like one big pile of memory. And this is apparently pretty good in terms of like fragmentation caused by, like all of your blocks will be allocated apparently like reasonably close together. But if your block size, if you're like, I'm going to split by like, if it's powers of 2, you can imagine that like a 10-byte allocation will take a 16-byte block, which means that you're going to have some sort of like wasted space due to that. But I don't know what the fuck I'm doing. This seems like kind of reasonable. So I would kind of like to try this system and see what happens if we do that. You know? You know? So that means that we're gonna have to have like some sort of like min size and some sort of like max size, right? I think that uh let's think about this. We're gonna have some sort of min size, some sort of max size. We're gonna start with a pool of max size, okay? And as that thing gets allocated from, we're going to split off pools of smaller sizes. That seems reasonable. Seems reasonable. So now the question is how do we store those pools? Because again, what you would naturally want to do is you would be like pools. And you'd be like, I have, maybe like a fixed amount of pools, and each pool is like a list of free blocks or something, right? But you can't really use an array list here, I don't think, because that array list like needs dynamic memory, which we don't have yet because we are the allocator, right? So like, what do we do? What do we do? We could, if our normal allocator stored its data with the bump allocator, right? Let's think about it like that. Let's just say we implemented it that way. We could say that we have, a pool item, and he's going to have like a next section. And in here, maybe we store like some amount free list, right? You could do something like this, where I have, here are my segments. I guess it's like maybe our free list should contain like a start and an end. Okay, that seems kind of reasonable, right? So we have some item that has these things, and then we could like allocate pool items from the bump allocator. That doesn't sound too crazy. And then we just when we allocate these things, we have to be a little bit careful because we want to allocate something that's a line of and size of the pool item, but this stuff is kind of going to live in line, which is kind of weird. But that's okay. We can kind of figure that out. So I guess our allocation is going to be like free list plus pool item. I guess is going to be something like that. So you store like this tracking thing at the beginning of your allocation plus the actual data. Yeah. Okay, so then if we were to do that, then we just say that we have our pools, and each pool is going to have a pool item? Okay. And I guess actually here, we want to say size here. So how much of this like free list is actually in use right now? Okay, sure. Seems reasonable so far. Maybe we start without doing the buddy allocator system. Let's just start doing like the dumb stupid system where we just put things in order and kind of see how that goes, and then we can kind of like work our way up. So we'll call this what was the name of that thing? Sequential fit. Sequential alloc. Maybe no, we'll just call it normal. It's fine. We can come up with better names later. Dude, my phone is gonna fall to my pocket and it's pissing me off. Okay. So I guess that means that we're going to have one thing that's like free list. And this is going to be a pool item. And I guess our initial pool item is like free list is empty. Next is probably optional. We might not have a next. So we can kind of do like this, right? So this is kind of like our default state. Okay. Then, as we allocate, we don't even really have to track our allocations. I guess we do. We probably need to track like, we probably need to track this, like the pages that we've allocated or the blocks that we've allocated, like we did in the, like we did here. We probably want some way to track blocks and where, maybe that's just it. So maybe we'll call this free item. And maybe we can kind of do the same thing with like blocks. So we're going to have, you know, blocks here are going to just be an array of, you know, we're going to have the same block thing here. I guess we can pull that block definition out to the top and return a block here and take in a block here. That kind of makes everything nicer. Okay. So then we just have like blocks here, boom, block. This is the size of our block of blocks, and the next block item. Okay. Maybe this is even like a block list. Okay, so our free list is gonna have, you know, free list, and our block list is gonna be a block list. That seems reasonable so far. Okay, so now when we allocate, we're going to first look at the free, I guess we look at the free list and we just take some data out of the free list. Okay. So let's, I wonder if it's possible for us to kind of treat this like one thing. That'd be kind of nice. Okay. Hold on. This is we're getting somewhere. We're cooking. So we push a range into this thing, right? Here he goes. If this is full, how do they do this in like the typical array list? I guess they kind of like flip this idiom on its head. They call this capacity. Yeah. So this is kind of like, it's fine. Okay. So if size, this needs to have self. And here it's like if self size is equal to self items len. I guess calling this items seems fine. We need to like move on to the next section. So list is self, I guess. And maybe this is even like a nullable free list. Pointer to a free list. Okay, sure. So this starts as self, and while list is not equal to null, we probably do something, right? So we like, I guess on push, maybe we'll just call it insert. We won't claim to have any order here. So we literally just look for the first list that we have that has room for this thing. That makes sense. So here we can go while size is equal to items len, list items len, list is equal to list next. Okay. Or else we need to do something. Here we need to like allocate a new list, right? That's kind of what we have to do here. But we haven't figured that part out yet. Okay. Then at the end of this, we just say that list items size is equal to range and list.size plus equals 1. Okay. So this is like, we can hop through these like connected lists that are linked together. Cool. Now we just have to figure out how to allocate a new list. So I guess we're kind of saying that this thing is going to use an allocator. And it would be sick. It would be sick to like, I guess it's fine. The bump allocator will work fine. The bump allocator will work fine. So here we just need to figure out what size we need to allocate. So we need to allocate a new free list, right? But we also need to allocate the new data for the free list, right? And so I guess what we need to do is we are aligning, we'll kind of like create this data so that we have the free list at the beginning followed by data. That seems reasonable to me, right? And then the free list will point to the next one if there's more than one. That seems pretty reasonable to me. So how do we determine that? We need the alignment of the data. We need the alignment of the free list. So surely we need the alignment of range, right? Because that's what these items are. And we're gonna start. Okay. So our alignment, our length of stuff is going to be size of the free list plus align forward. Yes. Align forward the size of the free list to the alignment of the range. Plus the size of the block. So like num items per block. I'm pretty sure this is right. Then we can do like allocate with options. Maybe it's even just a raw allocate here. Aligned allocate. Raw allocate seems kind of fine. It's kind of we're being a little tricky here. So we have our allocated len with the alignment. It's math log 2, the alignment of align of free list. I believe that's what they want. And then ret adder is kind of weird. Is there a way to do this without, like, is there really no, like, yeah, it does seem like if we want to batch allocate data and thing, But I guess we could just allocate them individually. There's no reason why that doesn't work. This is essentially what we're doing. I'm such a dumbass. Okay, wait, hold on. Next is just the alloc create a free list. Yeah, I'm way overcomplicating this. And then items is just alloc. Yeah, of course. This works great. This is what the fucking point of the allocators are. Num items per block. Uh-huh. Yeah, that's great. Except it's the other way around. And then it's next. Items equals items. And then list next equals items. Is equal to next. And then we break block next. Yeah, wait, this is hype. This works great. So this is supposed to be, well, list size equal to these things. Oh yeah, this is perfect. Alloc shadows. Oh sure. Fine. And then here we just need like num items per block is like 100 or something. We're willing to allocate 100 of these at a time. We could even do like every time we grow, we double in size or something to be like, look, if we ran out last time, we'll probably run out next time too. Right? You could do something like that. But this is fine. We'll just do them in blocks of 100 for now. Okay, this looks like we're getting some sort of like stable array list. This kind of like, it feels like what we're making here, where like the elements in the array list have static locations. So it looks like we're kind of doing like comp time t is going to be our element type. Right, and so we can kind of return this thing here. Range is now t. Size is still usize. Next is self, I guess. Okay. Range, here's elem now, t. And I guess this is just like stable list. Uh-huh. Okay, this is self, t, and elem. Okay. Cool. Now, we don't really have wait, yeah, this is fine. This is fine. So this is only growable. This guy's not capable of shrinking right now, but that's okay. We're cool with that. So now, this free list and block list just becomes stable lists of range. So this is a block, and this is stable list of range. Oh yeah, that's pretty hype. Let's just check that this stable list works, right? So let's go back to using our bump allocator down here for a second. And let's turn this into a stable list of usize. And let's just kind of see what that does. He has no function in it. Yeah, that's because we ain't no bitch, dude. Yeah, that's true. So here we're inserting now, and we're using the allocator here. 107 is pissed off because I guess this needs to be a pointer to self. And now that's kind of hype. So we see that all of our block lengths are the same,
we have a total allocation of 40,000, wasted space 6,000, and what are we expecting here? That we have 4,000 times 8, 32,000. So if we have wasted space 6,000, cursor 3312, that's about 9 plus which makes this about right? This is about 9, 40,000 minus 9 is about 32,000. So this is like a lot less overhead. And so can we just check now that if we were to like iterate this thing, this is not what we want now. AL items is no good. We want an iterator. So this guy's going to be like, I'm going to look at this first free list, sure. But what about next free list? So this is going to kind of have like the same concept where he's going to have a list that has self. Okay. On IDX is 0 into this list. And his next function should go. This is going to return a T. And self is iterator. Cool. So he's going to be like, if self size equal to self list items size, return null. That's our out. No. If this and oh no, that's fine. Yeah, so we return maybe we return a pointer to this thing. That's probably a little bit nicer. And our return value is just list items at index. Boom. Then we just advance this thing. Now we have to be a little careful. It's like if we do self index plus equals 1, this should be index here. If self index is equal to self list items size, we do a greater than or equal to here, and we say self list is equal to self list next, or else nothing, or else empty. Yeah. Self index equals 0. Okay, so now if we make a stable list of like 50 elements, and we go, we need to make an iterator here, so we need some sort of way to create this thing. Okay, then in here we go like while we get something next, we print the thing. Okay. No member name size, true. No member name size, true. Stable list does not support that. Fuck. I guess we can just return red here as long as our index is increased. Yeah, I think that's fine. Expected use size, so can we do pointer like this? Okay, and then while IT next. Okay, so that's not good. This is not behaving the way that we want. This insertion is not working. Why not? Why not? It means that this is immediately exiting. Because here, if the first list is empty, we replace it. We don't always, yeah. We have to go
if list items len is equal to 0, we just say list is equal to next, else this. Yes. It's something like this. There we go. Okay, stable list now working. And if we go back to 40, 4,000, do we see numbers that look like they increment from 0 to 4,000? That looks like it's kind of behaving correctly, which is hype. And then now we go back to looking at the state of the allocator after. And even doing the reset, maybe? Yeah, it's pretty hype. Hype. Okay, so now we have this way to build on top of our shitty bump allocator to make our normal allocator. That's hype. Hype, hype, hype. We barely even have to think about this. We are going to eventually have to figure out how to remove from this thing. But we'll tackle that as we need to. So somewhere, I guess, we were probably like sometime before now. We were like stable list. All right, and now we're back on trying to reuse freed memory. Okay. So what happens? On allocation, we have to check the free list. So free segment iterator. We need self. So this is a pointer to a normal alloc from pointer cast, align cast of context. We say that we have some form of free list iterator. And while we go over each segment of this thing, we have some range. Now, if this range supports allocation, I guess we could just try. If this thing succeeds, we return it. That seems kind of hype. That seems kind of hype. And then if none of the ranges support it, we need a new range, right? So if we get to the end of this thing, we need to allocate a new block. Map block. And the tracking is not done from this block, so we don't have to do anything but try to figure out the like aligned size of this thing. So I think we'll just do the same assertion here where we expect that that their alignment is like less than our alignment, and then we can just be like map block len, right? Okay. So now what? I guess we say we have some block, and we have to insert that thing in the block list. Okay. So we have like our bump allocator, probably. Something like this. Something like this. Which means that we probably have like a bump allocator here. Something like that. And we insert the block. Simple. And then we also do the same for the free list. So we go we have a new range now that goes from block. Why are the ranges U sizes? It's almost like these should be pointers. That's kind of how I'm feeling right now. That's how I'm feeling. So here we're looking at the beginning of the block. And something like this. That's kind of how it's feeling. Zig jump scare. I don't think there's any jump scares happening here, dude. That feels kind of reasonable. And then we just have to jump back to this part. Or we just assume, since the alignment here is fine, this is block 0 plus len here. And then, yeah. And then we return block pointer. I guess block pointer here makes more sense. Everywhere we're doing and block 0. Okay, yeah, that seems reasonable. And then where is like the chance for null? It's that this can fail. All right. Wait, that's kind of hype. That's kind of hype. So I think all we have to do is figure out if we can allocate from this range. So can we do like start this and like this, and then replace this guy here with some start and end? Then all we have to do is try to allocate from the range. Right? And this is going to return, you know, something like this. So self is a range, and then what are our arguments? It's like length and alignment. Okay, and then we align forward log 2. Probably we go like self, we probably do like something like this. Int from pointer. So we align forward the start to pointer align. Align start. And then we like, this is as a U size, as if you will. Align start. If align start U plus len is less than int from pointer self end, otherwise return null. Okay, so in this case we fit. Probably less than or equal to is probably more correct. Then we return, we do self start is equal to, I guess aligned and U is this. Like this, we get the end from this thing. Then we use that here, and then we cast it back here. Yeah, hype. Hype, hype, hype. Then, you know, in an ideal world, we remove this thing from the list. You know, if range empty, remove. But for now, we will just kind of keep doing it this way. All right, seems reasonable. So can we now use normal as our normal alloc and extract the allocator out from this guy? And let's just see if he behaves the way we want him to. He does not, 218. Because this stuff is a problem. Let's just do catch unreachable here because I don't want to deal with it. If this happens, then our allocator is just in like a fucked up state. There's a way to do this correctly, but whatever. Expected U8 found V's. Can we just change these to that? Okay. Then our function alloc somewhere implicitly returns. I don't know which one. 175. He's pissed off because of this thing implicitly. Well, oh, sure. Fine, if you're gonna be like that. Okay, so now he's just segfaulting, which means that we're doing something fucking stupid. This is actually happening on insertion here, which is into the array list. Okay. Sure, so this is in our allocator implementation. It's not in the block list stuff yet. It's alloc bytes with alignment here. From where is like R code in here? 150. So it's coming from our stable list insertion, which is kind of surprising because we tested this for ourselves. Wait. Oh, we're dumbass. Oh, I see. This is using the normal allocator under the hood. Okay, can we use an array list here? Because this was confusing. And then this is 4 AL items like this. Okay. Let's try that. Okay, so that also segfaults. That makes sense because our allocator is fucking broken. But now hopefully we have like something that's less confusing. So where is like main in any of this? Here. So at 237. Okay, sure. Oh, it's probably the mem set after they get our stuff out here is probably what's happening. So we return something, and he's like, no, 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 that's no good for us. Which is just segfaulting. Okay, can we GDB this and like wrong fucking file? Okay. So, right, this is coming after raw alloc. That makes sense. So I guess we probably want a breakpoint in our allocator function and just kind of see what's going on. Okay, so here it looks like we did not successfully find any ranges, which makes sense because our free list has nothing in it. We map a block, which is in fact reasonable, and then we just return the block pointer. Okay. So does he crash here? No, that one's fine. Okay, so it's probably when we're trying to take something that was in our free list and return and use that. So this guy's probably broken. So we need to breakpoint here. Okay. So can we like print the range? So we have something that's like from here to here. Except this guy's kind of claiming that that's not valid. Which is fair because the end is one past the range. That's how we structured this stuff. So can we print self end minus self start? We are a little bit less than one block. Totally reasonable. Okay, so can we then see what we're returning here? First of all, is this the failure? No, there's a lot of these before it becomes a problem. It's the length 2040, Okay, so we'll restart and we'll keep going to length 2040. And let's just take a little peek skis as what's coming out from here. Because we probably have just done something stupid. Can we... okay, so our aligned end is... Oh, are we just fucking stupid? Start here instead of end? We should be checking if the end is in range. We're dumbasses. Much better. Much better. Okay, so this is now reasonably working. And it would be nice to get some sort of, like, information out of this thing. So we actually haven't even done any reuse free memory yet. This is kind of like allocator that supports free. We haven't gotten there yet, but we have at least done the allocation side of this thing. Can we inspect him a little bit? I want to know what his current free list looks like, maybe? And his block list. I'd be interested in both of those things. So can we go like for var free iterator is normal, free list iter. And can we just like iterate this thing? So while free iterator next, let's take a little peek. So this is a range, I guess. Free range. I guess we'll do it like this. Free range eggs. Okay. Then I guess we are going to look at the allocated blocks. So how many blocks have we kind of yoinked out of this guy? This is block list, I think. Yeah. And what do we want to look at from the block? I guess just like the size of the thing. Block size, like this. Okay. Fuck. This probably has to be... Can I do pointer here? Can I print pointers in this language? Print X pointer? Can I print pointers in this language? Any? Okay. Okay, so it looks like we have some free ranges in here. It looks like none of them are quite full, but a lot of them are like, we didn't have room for this stuff. Right? So that kind of makes sense because all of our allocations have been pretty big so far. So I wonder, it would be kind of cool to see if we allocate a new thing here, if he comes out of the first free list, right? If we allocate like a couple ints, right? If we go like alloc 4 I32s, right? I would love to see I32, like, you know, ints. I would love to see that the pointer to this thing comes out of the first free list. That'd be kind of hype. Right, that'd be sick. Ints pointer. I don't know what the fuck that was. All right, let's try it again. Start print a pointer. Ah, I see. So here we are seeing exactly what we were hoping for, right? So we had a free list that started at 7FF, 7FF, 8C88, and now our ints, I32s, come from that guy, which is hype. That's so sick. That is so cool. Yeah, it's sick. Okay, cool. So now all we have to do is like implement free, right? All we gotta do. All I wanna do. Bum, bum, bum. Okay, so what are my arguments here? Buff, buff align, ret adder. Uh-huh. And what does the V table say about this thing? We gotta read. Buff len must equal the recent length returned by alloc.
Given a successful resize call, buff align must equal to the same value it was passed as the pointer align parameter. Ret outer is optionally provided. Okay. Interesting. Wait, so is this just not possible? Because if they gave us, they allocated us a length and an alignment, right? And we had like the start of our area. We like moved we moved a pointer forwards to fit that. Like we had some segment of memory, and he was like, I am this segment. And then we're like, okay, but like the length, we need like a length aligned to like here. So how do we know this space here to return it back to the free list? I feel like we don't. We don't have that information here. Which means that we need to track it? Is that crazy? We need to like write down what we have previously allocated and then find that just to undo it? No, there's no way. That's insane. What we could do is we could just say, look, no matter what, whatever we told you the length was, it's 8 bytes longer. So every time we give out an allocation, we give them a little bit of extra space so that we can tie back where it came from. Which means that like maybe overall that's like more wasted memory, but it because like everything that goes out has an extra 8 bytes on it. But also like maybe that's the only way. Or maybe we could get away with maybe an extra 1 byte. Because what are the chances that it's over 255 bytes away? Pretty slim. I would bet maybe not, right? So maybe they ask for this. Yeah, back in this example, we have this block. They ask for something that's this wide, but it has to be aligned here. And we give them this, but we also kind of just give them 1 extra byte. And in this 1 extra byte, we write how many bytes back this was. Which probably will effectively use a lot like more memory because the next guy's going to be aligned in a way that like this doesn't fit nicely anymore. But that guy can go fuck himself. Yeah, let's do that. Let's do that. So when we allocate, we're going to do len with tracking equals len plus 1. Then everywhere that uses len, we become here, len with tracking, len with tracking, len with tracking. Okay. Then here we go. Ret at len is so here it's like block at len is equal to 0, and then we have to do the same tracking here where we say yeah, it's like ret at len minus 1 is equal to align start u minus start u. Yeah. Cool. Cool. So let's just make sure everything else still works.
175 is pissed off because we have to return ret. Okay, so everyone's still happy. Nothing's crashing. And now on free, we should be able to be like, Paul, greetings, streamer and fellow streamies. Thank you, thank you. Hello, hello. Thanks for the sub. Much appreciated. Okay, so first of all, we gotta figure out who ourselves are. We don't give a fuck about this ret adder. We do give a fuck about the alignment and the buff. We probably don't even care about the alignment, to be honest. We're kind of assuming that, like, it's fine. It seems like the fact that they're giving that alignment really makes it sound like there's some way to utilize that. I just don't know what it is. So we'll just do what we did. So we'll say a real buff is equal to okay, so we say like start adjustment is equal to buff pointer plus buff len, and we dereference that. Okay, seems reasonable. Then our like actual buff is okay. So the free like buff end is buff pointer plus buff len, okay? And buff start is buff pointer minus start adjustment. And then we need to like we make our free list. We insert a thing that goes from buff start to buff end. Seems kind of reasonable. Seems kind of reasonable. Unknown length. Index syntax required for unknown. Oh. Okay, so this is allowed because I'm intentionally bypassing the like bounds checking, which makes sense. This guy needs our bump allocator. Like that. And then area is ignored, so catch unreachable will crash. Okay, so now the question becomes, if we start just like spam allocating and deallocating things, will we correctly end up in the right spot? So first of all, we'll do our existing test. It looks like our existing test was working fine, right? Because there's no freeze, nothing's changed. But now can we start doing some trickery? So, you know, 100 I32s. We'll allocate these 100 times. And then we'll free them. I guess at the end of all this, we want to inspect our state, which we deleted like dumbasses. Okay, let's actually just do an ALD init here, right? Let's see what our free lists look like if maybe we do our free list before and after dinit. So maybe we call this like dump allocator. Okay. We'll call this normal. Okay, and then we dump alloc normal here and here. We probably need to put an ampersand here. Okay, so before, it does look like we have gained some area here. So yeah. So we have free range eggs from 74,000 here, which is this guy, and then we've just tacked on an extra one here. So probably what we should do is we should also try to merge free lists to like avoid fragmentation. But I think that's a problem for tomorrow. So I think what we're going to do tomorrow is probably try to start like visualizing fragmentation here, and then try to make sure that like our free list does in fact like collapse itself back down into one free list later. And then maybe we can start looking at like buddy, we can start looking at like the like buddy implementation as well. What was that thing called? Buddy memory allocation. So we can start trying to do something a little bit more intelligent to reduce the fragmentation. But it looks like at the very least for now we did gain, what is this, p this minus this, by de-initializing our vector. Really? It does look like we gained 36,816 of memory, which is bigger than the 32K that we expected to need, right? Which makes sense. So yeah, pretty sick. Pretty sick. I think I'm happy with that. Oh, I guess this is like wrong to some extent, huh? These ranges overlap, which is really bad. That's really bad. But we will tackle that tomorrow. So, thanks for watching, guys. If you like what you saw, we stream most days at 12:30 Pacific time to 4 o'clock Pacific time. It is 4:20 now. Blaze it. Peace up. Oh my god, shut up. So, if you're watching live, you should expect to see us online from somewhere around 4 hours ago to now. If you're watching live and you're like, I want to follow your projects, but I can't watch every day, but maybe I can have time to catch up. There's a YouTube link in the description. VODs, the 2 to 4 segment show up in here. So this is kind of like the focused like thing with a to-do list type shit. If you want access to VOD access to the 12:30 to 2 segment, you're going to have to, put money where you find appropriate. So Twitch, Patreon, or YouTube. You can, sub or join on all of those to get VOD access, or you can catch them live. Today's happy hour segment was ranting about C++. We implemented the world's shittiest C++ container and then screamed at all the problems that are there are that why I don't like it, as well as like a little bit of like B-tree stuff. But you shouldn't need to, if you don't watch the 12:32 segment, you're not really missing anything too important. None of our the long-term story of the project is not lost in there, so don't feel pressured. Otherwise, I think that's all I got to plug. YouTube, peace out, and Twitch, let's find someone to raid.